Okay, just continue. Okay, so the different part is the 2 to 3 and 4 to 1, constant regeneration. What does it mean by regeneration? Regeneration, internal heat transfer from the working fluid to the regenerator, internal heat transfer from the regenerator back to the working fluid. Okay, regeneration means that we use the heat from the higher source temperature to reheat the working fluid at the colder part. Okay, so in a cycle there's always one part is at highest temperature, one part at lower temperature. So the higher temperature part is for this Stirling cycle is 2 to 3. Okay, and the lower temperature part is 1 to 4 to 1. Okay, the same as this one, 2 to 3, 4 to 1. Okay, high temperature, lower temperature. Okay, so what the different thing about Stirling cycle, uh it use the heat. Okay, because after the process of heat addition, the constant expansion at point 2, the working fluid is at high temperature. Okay, at temperature TH. So in order to save some sort of to save energy to heat up the cold temperature from point 4 here, from TL, we reuse the heat from the working fluid from TH point 2 to heat up a bit the cold part. Okay, so this is what we call the process regeneration. Since the process is a cycle, so we can reuse the heat from the higher temperature source to heat up added to the lower temperature level here in the working fluid, the same working fluid. Okay, we just reuse the heat. Okay, so it can minimize the heat, the required input, the Q in, minimize Q in. So if we minimize Q in, we can increase the efficiency of the cycle. Okay, by reusing the heat. Okay, the heat from the same working fluid to reheat to heat up a bit the working fluid, the same working fluid at a lower, from the lower temperature TL. Okay, so that is the different part of the Stirling cycle compared to Carnot cycle. So the process of the regeneration occur at constant volume. Means that the volume of the working fluid doesn't change during this process. Okay, we only give transfer the heat. Okay, the heat is transferred. Okay, so that is the different part of the Stirling cycle. We have this regeneration, and the regeneration process is occur at constant volume. Okay, a regenerator is a device that borrows, somehow it's like it borrows the energy, pinjam, from the working fluid during one part of the cycle and pays it back without interest during another part, something like that. Okay, in simple word, somehow we like borrow it from the higher temperature source and give it to the lower temperature source, and then since it is cycles, so it will like a payback balik. Okay, during another cycle. Okay, and then Ericsson cycle. Okay, Ericsson cycle. Uh, the process is like very much like Stirling cycle, except that the two constant volume process are replaced by two constant pressure process. Okay, so Ericsson, it also has regeneration, but this time the regeneration occur at constant pressure. Okay, instead of constant temperature, constant volume, constant pressure. Okay, so this is the schematic diagram, PES and PV for Ericsson cycle. Okay, so this one, how do we execute the Stirling cycle? Okay, so one thing interesting about this Stirling cycle is that it is an external combustion engine. External combustion engine. Okay, what do you mean by external combustion engine? Is that the engine, okay, the Stirling cycle, the engine can run with an external heat source. Okay, if we say internal combustion engine ICE, we will mention ICE, right? ICE for usually for cars or vehicle. ICE, that is internal combustion engine, means that the combustion process occur internally, inside the combustion chamber, inside the burner, internally the process. Okay, so the heat source must be the fuel and the oxygen for the combustion process to occur. It must occur internally within the device. Okay, but for a Stirling cycle or Stirling engine, the engine can run with an external heat source, as long as there is an external heat source with enough temperature, uh, and the engine can start to run. Okay, that is the best part about this Stirling cycle, because we don't need to conduct the combustion process inside the engine. Okay, as long as we have a different temperature, a finite different temperature between the head of the Stirling engine and the heat source, okay, the engine can run externally. Okay, for example, if you you have the piston. Okay, so this piston act as the Stirling engine. Okay, and then you have like a candle. Okay, so this candle is your heat source. So as long as you put the candle, for example, okay, the head of the piston, kat mana ni? This one, I think. Okay, the head of at the head of the piston engine, you put the candle, and there is a heat transfer from the candle, the hot temperature, the candle, to the head of the piston. So the piston can start to expand or compress. Of course, expansion first due to the heat. Okay, so that is the interesting part about Stirling cycle. It is an external combustion engine, not internal combustion engine. So there is interest in applying this Stirling. So you don't need, as long as you have a heat source outside, enough temperature, cukup tinggi untuk for the engines to start to run. Okay, so that's why there is research that going on, okay, to apply this Stirling, because it has potential, a great potential. Okay, me myself, I'm doing research, one of my research regarding this Stirling engine. Okay, and then Aerothermodynamics, okay, the same as Aerothermodynamics. Also, we can run the Aerothermodynamics externally, okay, as long as we have the heat source. Okay, except that here Aerothermodynamics use constant pressure. Okay, so the calculation of the thermal efficiency of Stirling, Aerosol, and Carnot are the same. So it depends on the temperature, the higher temperature and the lower temperature only. It acts like a Carnot cycle. Okay, so as I mentioned just now, actually there are two more cycles, heat engine, Otto cycle, OTTO, and diesel engine cycle. But I didn't put in these slides, in this chapter, because it concerns more on the mechanical part. But if you are interested in it, you can just read it in your textbook, the main reference book, the McGraw-Hill. Okay, or other any reference book you can just choose. Okay, I didn't put it because I want to save time, of course, and want to focus more on for the aerospace application or power plant application. Okay. Okay, so this is the most important part. So we have Brighton cycle. Okay, so Brighton cycle is the one that we use for gas turbine engine and for aircraft jet engine. Okay, so aircraft jet engine, your aircraft engine operates based on Brighton cycle. Okay, Brighton cycle, remember. Okay, so Brighton cycle, the ideal cycle for gas turbine engine. The combustion process is replaced by a constant pressure heat addition process from an external source, and the exhaust process is replaced by a constant. Okay, this is for power plant. Okay, for power plant, gas turbine engine for power plant, for the heat addition process, we use heat exchanger. Okay, on my right hand side, we see a closed cycle gas turbine engine. Okay, so this is the main for device for a closed cycle gas turbine engine. Compressor, heat exchanger, turbine, and another heat exchanger. So the first heat exchanger is the evaporator, and the second one heat exchanger for heat rejection is the condenser. So the same as the just now, the normal heat engine. Okay, so that is the closed cycle gas turbine engine. Okay, for power plant to produce electrical power, mechanical power, kat kilang-kilang industri. Okay, for industrial purpose. Okay, another so this is the on the left hand side, this is the one that we use, the cycle that we use for aircraft engine, an open cycle gas turbine engine. Okay, for aircraft engine, it is an open cycle, not a closed cycle. Open cycle because after the turbine, after the working fluid exiting the turbine, it will be exit the nozzle. We have a nozzle, and then exit to the ambient. So we don't have the 4-to-1 process using the heat exchanger. Okay, so that is the different part, open cycle. So the heat exiting the exhaust nozzle will be rejected to the ambient. Okay. Okay, so this is the important part. We use this one, fresh air. Okay, fresh air from the ambient goes inside intake at the compressor, and then combustion chamber, combustion process, and then turbine expansion, and usually we have nozzle. Okay, to speed up the air, the working fluid, to a high speed gas flow. Okay, to produce thrust power. Okay, so this is how we calculate, evaluate the performance. Very, very important. This is how we evaluate the performance of a Brayton cycle gas turbine engine. Gas turbine engine, the cycle is Brayton cycle. Okay. So TS diagram, you can use TS diagram or PV diagram. So we focus more on the TS diagram. This one we will use a lot of time for propulsion next course, next semester. Okay, so this is the first energy balance, the first law of thermodynamics, the energy balance. So for the energy balance for Brayton cycle, so you have Q in, Q out, Q in, Q out. You have W in, W out, W in for compressor, W out at the turbine. So all of this equals to the to energy transfer by mass, which is enthalpy, H exit minus H inlet. Okay. So you can also calculate the Q in here using the enthalpy at point 3 minus enthalpy at point 2. Or you can also using the CPDT. This one we have seen last week. Okay, the TDS relation. CP, specific heat, and the change in temperature during the heat addition process in the combustion chamber here. Okay. And Q out, heat rejection. Okay, this is for closed cycle gas turbine engine. So H4 minus H1, CP, T4 minus T1. Always higher temperature minus lower temperature. Okay. So the thermal efficiency for Brayton, the desired output is W net, the thrust power. Okay. Over the Q in, the fuel, the combustion process occur in the combustion chamber. So that's why we want, usually we want to minimize the fuel, the consumption of fuel, right? We want to save the fuel, etc. Because by saving the fuel, we save the Q in. And if we save the Q in, we can save the thermal efficiency. Okay, so that's why we always focus on the saving fuel, etc. Okay, so and then we can also calculate using 1 minus Q out over Q in. Okay, if you don't have the value of the power of the work output, we can use Q out, Q in. Okay, and just develop the equation. So we get this. Okay, so we can rewrite Okay, before that, we for ideal gas isotropic process, last week we have seen this one. Okay, ideal gas isotropic process, we can write T2, the ratio of temperature equals to the ratio of the pressure. Remember, this is only valid for ideal gas isotropic process. Isotropic ideal gas process, only valid for that. So this is only valid usually for ideal cycle. So we can use this one, and it is also equals to this one. Okay, this side and this side. Okay, so this is P2 over P1 is the pressure ratio. Pressure P2 over P1. So we can, after we have rearranged the equation, etc. here, we can replace the P2 over P1 here, and we get the thermal efficiency of the Brayton cycle in terms of only the pressure ratio. Means that once we know the pressure ratio of the cycle, which is usually a parameter given to the cycle, once we know the pressure ratio, we can calculate the efficiency of the cycle without knowing all the temperature, W net, Q out, Q in, etc. Just depending on the pressure ratio. Okay, so if we sketch the graph of the thermal efficiency of the ideal Brayton cycle as a function of pressure ratio. So higher pressure ratio will end up results in higher thermal efficiency. Okay, means that if we increase the pressure ratio here, P2 over P1 or P3 over P4, we can increase the thermal efficiency. Okay, at one point, at one side. Okay, so this is the range of typical pressure ratio for gas turbine engine along 5 to 20 pressure ratio, and from 0 to 0.65 efficiency, 65%. Usually 50% to 65% the efficiency of a Brayton cycle. Okay, the conventional Brayton cycle. Okay, so the two major application of gas turbine engine are, like I mentioned, aircraft propulsion engine and electric power generation for power plant. This is closed cycle. This is open cycle. Okay. Okay. So we our objective is to produce net power output. So net power output is the power produced by the turbine minus the compressor work that we need to give to the compressor. Okay, so the highest temperature in the cycle is limited by the maximum temperature that the turbine blades can withstand. This also limits the pressure ratio that can be used in the cycle. Okay, of course, we know that from this here, if we increase the T3, the turbine inlet temperature, this is the turbine inlet temperature because 3 to 4 is the turbine expansion process. Okay, this turbine inlet temperature. We know from the calculation here, if we increase T3, we can increase the thermal efficiency, right? But at the same time, however, we have a certain maximum value that the turbine blades can withstand. Okay, that is for according to the material used for the turbine blades. Okay, so turbine blade tu dia ada maximum temperature. Of course kita nak tinggikan dia sebaik mungkin sebab kita nak increase temperature. Tapi dia ada ni, sorry I speak a little bit. Okay, so so of course we want to increase the temperature the temperature turbine inlet temperature as much as we can because we want to increase the thermal efficiency. But however, the turbine blades has a maximum temperature that it can withstand. Okay, otherwise the material will be default. Okay, what's up? Okay, so it has limits. Okay, it has limits. This also limits the pressure ratio. Okay, so otherwise we will try to increase the pressure ratio as much as we can, as high as we want, but we cannot do that because it has limits. Okay, the air in gas turbine supplies the necessary oxygen for the combustion of the fuel and it serves as a coolant to keep the temperature. Okay, that is the combustion process. Okay, so that's why, before that, okay, so the development of gas turbine, okay. Okay, so research study has been done to increase the performance of gas turbine, of course. We will break at 11 a.m. Dah terlepas. Okay, 11 a.m. Okay, so of course we want to increase the performance of the gas turbine engine. So methods that that researchers, scientists have done in order to increase this performance. One method, one way is to increase the turbine inlet or firing temperature, like T3 just now, or increase the turbine inlet temperature, T3 here, okay, as much as we can, okay. Other way, increasing the efficiency of turbo machinery components, turbine compressor. Turbo machinery components are turbine and the compressor here. Okay, so we increase the efficiency of turbine and compressor so it can run more perfectly, something like that. Okay, if we increase the efficiency of compressor and turbine. Third method is to add modifications to the basic cycle. Okay, this is what we want to see in the later slides. We modify the basic cycle. Okay, we modify the basic cycle, whether we add intercooling, we regenerate it, recuperation, like just now, like Stirling cycle, Edison cycle, or we reheat the working fluid, we add the reheater. Okay, so there are several methods to modify the basic cycle in order to increase the performance of the whole gas turbine. Okay, of course, different method has different pro and cons. Okay, so it depends on what is our objective, what do we want as an outcome, what we want to optimize, what we want to prioritize. Okay, there is no one solid solution, okay, to improve the performance of gas turbines. Okay, so the deviation of electrical. So like the heat engine cycle just now, so Brighton cycle also have ideal cycle and actual cycle. Okay, so the ideal cycle, the straight line here. So you have the TS diagram, isentropic process, 2S, 3, 4S, and back to 1, etc. But we also have the actual cycle, the dot dash line here. So from 1 to 2A actual, 2A to 3 with pressure drop, 3 to 4A with the efficiency, mean that the process is not ideally isentropic, so it has some loss, efficiency loss, to 4A, and then back to 1. Okay, so this efficiency compressor depends on the 2S, the position of 2S and 2A. 2S, 2A. The enthalpy here, enthalpy of location 2S isentropic, and the actual enthalpy. Turbine process expansion. So the efficiency of the turbine depends on the location for A, the actual process, and the isentropic process. So we have the efficiency. So if we increase the efficiency, here, increase this one, means that if we increase the efficiency of turbine, means that the location for A approaching for S, okay, means approaching the ideal case, ideal cycle situation. Okay, like this one also, if we increase the compressor efficiency, means that the location of 2A approaching to S. Okay, so we have a higher efficiency of the compressor and turbine. So that is one way to improve the performance of the gas turbine cycle. Okay, one way that we can do, that can be done. Okay. Okay, so the third method is by doing modification to the basic cycle, okay, with several options. One option is by regeneration just now, okay, it's like the same as Edison and Stirling cycle just now. Okay, the same as the Edison and Stirling cycle just now. So gas turbine engine also can we can add regenerator. The temperature of the exhaust gas leaving the turbine, okay, exhaust gas leaving the turbine, the temperature 4 here, okay, temperature 4 here. is often considerably higher than the temperature of the air leaving the compressor. 2. Look at the T4, focus on the T4 and T2. Okay, T4, temperature of the exhaust gas leaving the turbine, T4, is often higher than the temperature of the air leaving the compressor, T2. Okay, T2 always lower than T4. T4 always higher than T2. We cannot have T2 higher. It's impossible. Okay. Okay. So therefore, knowing that, the high pressure air leaving the compressor, the high pressure air leaving the compressor, this is air at high pressure after the compression process, 1 to 2 compression process, can be heated by the hot exhaust gas in a counterflow heat exchanger, which is what we call regenerator or recuperator, because it recuperates the heat. Okay. So this temperature T2, okay, can be heated by using the heat, okay, that with at the higher temperature, leaving the exhaust gas leaving the turbine here. Okay, because if you don't have the regenerator process just now, if you look at the cycle, the combustion process Q in, okay, Q in is from 2 to SO2A, 2 to 3. 2 to 3. Instead, if we have regeneration, we can save this Q in instead of from 2 to 3, which is higher temperature, higher energy needed. Okay, we can save it by using the energy from the internal energy from the gas leaving the turbine to heat up. So Q in is only from 5 to 3 instead of from 2 to 3. Okay, so lower difference of temperature means lower energy use in the Q in. Thus, if Q in is lower, remember the thermal efficiency, if Q in is lower, then the thermal efficiency will increase. Okay, so macam itulah. Okay, so we save the Q in, or we save the fuel. Otherwise, we need more fuel to produce enough energy. Q in to produce enough heat, heat addition. Q in. Okay. Otherwise, if you use the heat, the temperature of the exhaust gas, this heat, and to heat up the air leaving the compressor, to heat up a bit to by regenerating it, this from the exhaust gas here, so we save the Q in. Okay, so this is like 4 to 6 is somehow the Q save. Okay, the Q that we save. Okay, something like that. Okay, so the thermal efficiency will be better, hopefully. Okay. Okay. Isn't the gas leaving the exhaust is burn fuel mixed with air and isn't 100% air? Okay. Yes. It is not 100% air, but we use the heat. It's not it's not the air mixed up. I mean, it's not the mixture of fuel and air mixed up with the air here. It is the heat. The heat of the exhaust gas that we use to heat up the air from the at point 2 here. You know what I mean? We don't mix the mixture, the fuel, etc. But we use the heat from it. Okay, transfer heat, heat transfer. Okay. Okay. Gas turbine. Okay, so that is how it can be done by using regenerator. Of course, there is pro and cons. The pro, of course, we can benefit, we can optimize the thermal efficiency. The negative part of the cons is that we need to apply another heat exchanger, so it will add more cost. Okay. More cost, and maybe it use it add more cost. And if especially for power plant, maybe it's not really a constraint, but for aircraft engine, it is a constraint, because it will add to added weight for the aircraft engine. Tambah berat, added weight to the aircraft engine. Okay, but in the end, depends on what we want to achieve. If we if our aim is more on the to really minimize the fuel, so so no matter how the weight of the how much the weight of the regenerator, so we are willing to add on to the weight of the aircraft engine as long as we can save the fuel. So we might consider this regeneration. Okay, regenerator. Okay. So for regenerator, the thermal efficiency, oh, this one. Okay, so the thermal efficiency of the Brayton cycle we change slightly from this is the original one, the basic cycle. So it will change slightly. Sorry, it will change slightly. The thermal efficiency of the regeneration, the whole cycle, we change to this. Okay, we change to this. So the efficiency, the effectiveness. Okay, for regenerator, for heat exchanger, we don't call it as efficiency. We call it as effectiveness, epsilon. Effectiveness of the heat exchanger regenerator is the actual performance, the actual heat that can regenerate, and the maximum heat regeneration. This is the effectiveness, like the efficiency of the regenerator. Okay, so and the thermal efficiency of the whole cycle with the regenerator becomes this one. Okay, after rearrange the equation. Okay, so this is the actual H5 to 2, 5 to 2. This is the actual regeneration process. Maximum 4 to 2. Maximum that if the effectiveness of the regenerator is at maximum, 100% efficiency, so we can use all the heat from the exhaust gas at point 4 to heat up the working fluid air from 2 to 5. Okay, so that is the maximum, but usually it is not the process is not 100% effective. So only in actual case, maybe we can only increase the heat from 2 to 5. Okay, this is the actual. Okay, and the whole cycle thermal efficiency, this is just efficiency for regenerator, just for the regenerator, and this is the thermal efficiency for the whole cycle. Okay, so the thermal efficiency versus pressure ratio, just now for the basic cycle we have this one, right, basic cycle. So but with regeneration, the thermal efficiency is higher with less pressure ratio. This time it is difference. If we, with regenerator, if we reduce the pressure ratio, we will increase the thermal efficiency with regeneration. Okay, so the parameter has changed. The focus of the parameter has changed. Okay. So the thermal efficiency depends on the ratio of the minimum to maximum temperature as well as the pressure ratio. It depends on the temperature and also it depends on the pressure ratio. Okay. Okay, before we continue, actually I don't have no much slides anymore, but before we continue, we'll take a break. Okay, so we take a break until 11:15, 13 minutes, around 30 minutes, okay? Okay, we continue. Okay. So are you guys back here?
Yes.
Extension, Afiq. Okay, okay. Actually, 11, there's 11. There are two more students who are absent. I don't remember. Oh, Omar. And the other one, don't remember. Okay, it's okay. 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 So the third method to increase the performance of Brighton cycle gas turbine engine. So the first one we have seen just now, regeneration. Okay, and then we also have intercooling and reheating. Okay, so but this is a combine of the of those three: intercooler, regenerator, and reheater. We combine all those three. Of course, this is maybe not the optimized option for aircraft engine, but for power plant, maybe this is the best one of the best method, okay, to increase the performance of gas turbine engine. Okay, so the function of regenerator we have seen just now. Okay, the function of intercooler. So intercooling. Okay, you always the location we place it between the compressor, at the compressor. Okay, so usually we have higher compression and lower compressor. Okay, lower compression process and a higher compression process, two stage, at least minimum two stage compression. So we add a heat exchanger which is act as a intercooler here between the two stage of the compression process, low compression and high compression. We add a intercooler. So what does this intercooler do? Okay, it can help to minimize the work input in the compressor. I think I've mentioned this last week. Okay, to minimize the work input in the compressor. So if we are able to minimize the compressor work, means that we save electricity. Okay, we save the work. Thus, we can increase the efficiency of the whole cycle. Okay, so you can look at the TS diagram here. This 223 is the process occur in the intercooling. So we intercool back. Okay, we cool back the working fluid from 2 to 3, decrease the lower down the temperature back to 3, and then recompress it again. Okay, 3 to 4, compress it again. So 2 times compression, 1 to 2 and 3 to 4. Between that we have intercooling. Okay, so by adding this intercooling, we we minimize the heat. Okay, the heat is safe. Okay, we exchange heat. The Q out is double here. Okay, we exchange heat and we lower down, lower the temperature, lower the temperature from 2 to 3. Okay, so and then compress it back 3 to 4. Okay, and then the same thing for reheater. Reheater is to maximize the work output from the turbine. Okay, so instead of just 6 to 7 and directly Q out, we heat up back, okay, the compression. Okay, to set from 7 to 8, reheat back. Okay, of course, by adding the reheater, we need extra Q in, extra fuel, okay, to heat up. But one thing, the benefit is that we can increase um, the maximize the work output from the turbine. Okay. So it is the expansion process occur 2 times, from 6 to 7 and 8 to 9. And the output is maximized, the work output. Okay, so a gas turbine engine with two-stage compression with intercooling, two-stage expansion with reheating and regeneration, and STS diagram here. Okay, so this is the combined example of combined cycle for gas turbine engine power plant. Okay, so we can also have multi-stage, okay, not just two. We can have multi-stage compression with intercooling, so less heat input, okay, to minimize more the compressor work input, or multi-stage expansion with reheating, okay, to maximize the work output, keeps the specific volume of the working fluid as high as possible during an expansion process, thus maximizing the work output. Okay, we can maximize the work output by reheating reheat back the working fluid and expand it again, multi-stage expansion. Okay. So if we look at here, as the number of compression and expansion stage increase, the gas turbine cycle with intercooling, reheating, and regeneration approach the Aerosol cycle. Remember, Aerosol cycle just now, the regeneration process occur at constant pressure. So if we do the multi-stage compression or multi-stage expansion, the process in the expansion and compression tends to be at constant temperature and pressure here. Okay, so it resembles approach the Aerosol cycle. Okay, ideal jet propulsion cycles. Okay, so for aircraft engine, now we look at the aircraft engine. So aircraft gas turbine operates on an open cycle. Okay, just now all of this closed cycle for power plant. Okay, to produce electrical power, mechanical power, etc. Okay, now we look at the ideal jet propulsion cycle. So we have aircraft gas turbine cycle operate on an open cycle. Okay, so this jet propulsion cycle differs slightly from the simple ideal Brayton cycle because the gas is not expanded to the ambient pressure in the turbine. Okay, because for Brayton cycle, for the ideal Brayton cycle just now, we have the cycle is closed cycle. Okay, the process from 4 back to 1 in the condenser. But here for ideal jet propulsion, the exhaust gas is being expanded directly to the ambient, to the atmosphere, open cycle. Instead, they are expanded to a pressure such that the power produced by the turbine is just sufficient to drive the compressor and the auxiliary equipment. Okay, we don't need the condensation process. Okay, the thrust power produced at high speed gas flow, okay, enough to drive back the compressor and other auxiliary equipment, the air control, okay, surface, etc. Okay, the net work output of a jet propulsion cycle is zero. The gas that exit the turbine at relatively high pressure are subsequently injected in nozzle to provide the thrust to propel the aircraft. Okay, so for jet propulsion cycle, the aim and the objective is not the network output like the electrical the power plant just now. The power plant is to produce electric power, to produce power. So our main focus is the work output. But here for the jet propulsion cycles, even though we use the same cycle, Brayton cycle, but the objective is not to produce work output. The objective is to provide thrust so that the aircraft can propulsion. Okay, to accelerate the gas in a nozzle and to provide thrust. So that's why we focus more on the thrust power produced. Okay, to evaluate the performance of an aircraft. So aircraft are propelled by accelerating fluid in the opposite direction to motion. Okay, we after the turbine, okay, in the power plant we don't have nozzle, but for aircraft engine jet propulsion cycle we have a nozzle. Okay, this nozzle, it can help to increase the velocity, kinetic energy of the air, okay, to a high speed gas flow. So we can accomplish we can produce propulsion power to propel the aircraft. Okay, the thrust power. Okay, that is more important. This is accomplished by either slightly accelerating a large mass of fluid, propeller-driven engine, or greatly accelerating a small mass of fluid, jet, or both, turboprop engine. So these are the types of the aircraft engine. We have propeller-driven engine, turboprop, or turbofan, turbojet. Okay. So the high temperature and high pressure gas leaving the turbine are accelerated in nozzle to provide thrust. Okay, so with the internal heat, the internal heat, the working fluid at high temperature and pressure exiting the turbine is converted to kinetic energy, okay, to propel the aircraft engine. Okay. Okay. Accelerating a fluid in the opposite direction to the motion. So another principle that is used in to propel the aircraft engine is the Newton third law. I think Newton third law. Okay, Newton third law. It says that whenever a material, a solid, an object, whenever we have a force in one direction, there's always another force in the opposite direction, something like that. The Newton's third law said, right? There's always one force and another force at the opposite direction. Okay, so that's how turbine, that's how jet propulsion cycle process is conducted, is done as well, according to the Newton's third law. Okay, after combustion chamber, it will create a force, okay, in one direction, and due to this force, automatically with the Newton's law, okay, it will inject, okay, another force in the opposite direction, and this will create motion of the aircraft. Okay, so this is based on the aircraft are propelled by accelerating a fluid in the opposite direction to motion. This is based on the Newton's third law. Okay. Yeah. Okay, so this one, so we have the thrust propulsive force power. Okay, so we need to evaluate the performance of aircraft. One of the important parameter is the thrust power, F, or sometimes it is written as T, thrust. So how to calculate thrust? Thrust is, it is like the second law Newton, F, the sum of force equals to MA. Okay, so this is, or M dot V. Okay, so this is where it came from. Okay, the sum of the thrust equals to the momentum, the change in the momentum, Newton's second law. Okay, so we have this one, mass fluid of the air. This is ideal case. Velocity of the working fluid at the exit minus the inlet, and then we have propulsive power multiplied with the velocity of the aircraft. Okay, so we can calculate thrust force or thrust power. And the propulsive efficiency, okay, unlike for gas turbine power plant cycle, we calculate the thermal efficiency. But for aircraft engine, we'll calculate the propulsive efficiency, because our desired output this time around is the propulsive power. We want to create propulsive power as much as we can to propel the aircraft. Okay, and so our required input is the energy input, which is the energy added to the combustion chamber, the fuel, and to burn the fuel. Okay, the process in the combustion chamber, combustion process, and this is the thrust power produced. Okay, so that's how it's the same TS diagram, for ideal case, but the calculation is different. Okay, we use thrust and we focus on the propulsive efficiency. Okay, so and then this is the ideal turbojet cycle. Okay, this one you will learn more in detail in propulsion. Okay, but at least you know by now, this is the schematic diagram of an ideal turbojet cycle. Okay, for aircraft engine. Okay, so 1 to 2 you have diffuser. Diffuser is like, the function is like the opposite of the nozzle, is to decrease, to slow down the air at the intake. Okay, and then we have compressor to compress the air, And then the burner section, the combustion chamber. Okay, 3 to 4 combustion chamber. Fuel is being added here, injected here, and so the air mixed with the fuel will burn and the combustion process, and then will produce power, produce fluid at high temperature and pressure, and then 4 to 5 expansion, and then before it being rejected, it will flows into the nozzle, because the nozzle can helps to accelerates the working fluid to a high speed gas flow, because we want to produce propulsive power force. Okay, 5 to 6. This is the basic ideal turbojet cycle. Okay, so instead for just now gas turbine closed cycle, we only have compressor, burner or combustion chamber, and then turbine, and then evaporator. But here for aircraft engine, we have diffuser and we have nozzle, but we don't have condenser. Okay, so I think this is the second last. Okay, so again, modification of turbojet engine. So turbojet engine is like the first aircraft engine cycle produced by the scientists, researchers. Okay, after that research has occurred, etc. So the turbojet engine has been improvised. So one of the improvement that have been done to the turbojet engine is by creating another aircraft engine, which is called a turbofan engine. So this is what usually use turbofan engine for our civil aircraft engine. Okay, we use turbofan engine. Okay, so it is being modified from the actual initially turbojet cycle, turbojet engine. Okay, we modify it to increase the performance, and we create this turbofan engine. Okay, so both propeller-driven engines and jet propulsion-driven engines have their own strengths and limitations to combine the desirable characteristics of both in one engine. So, in order to optimize the performance, so they create this turbofan engine by adding the propeller part, which is the fan, and the initial turbojet engine. Okay, so because we have a propeller engine, the normal propeller engine, and then we have turbojet engine. So we combine both of these characteristic, and we get this turbofan. Okay, so we add fan. Just now, the ideal turbojet, we don't have fan, we only have diffuser and compressor. But with turbofan, we have fan. Okay, the function of the fan, the process is kind of like the compressor. It compress, increase the pressure, etc. Okay, just that fan will add extra mass flow rate. By adding the propeller, we add extra mass flow rate intake to the jet engine. Okay, extra mass flow rate. There is a bypass flow here. Bypass. This is the flowing the air working fluid flowing in the core engine, and the pink one is the air flowing in the bypass duct, the fan exhaust and turbine service. So we have two flow, okay, two flow of for the fluid. Okay, so it has excess air. By adding this excess air, we can increase the performance of the turbofan engine. Okay, so the most widely used engine in aircraft propulsion is the turbofan engine, wherein a large fan driven by the turbine force a considerable amount of air through a duct or coil. This is the duct, the extra duct, okay, bypass duct surrounding the engine. So we add extra air intake. Okay, this is an example of model jet engine, Boeing 777. Okay, so this is the turbofan engine. Okay, air inlet, we have fan, low pressure compressor, high pressure compressor, so two-stage compression, combustor, okay, two-stage turbine also, low pressure turbine and high pressure turbine, and then thrust exiting the nozzle. Okay, and this one is turboprop engine that usually is used for, sometimes it's used for short distance civil aircraft engine. Okay, for short distance civil aircraft, for short distance sometimes we use turboprop. For long distance we always use turbofan. Okay, so turboprop or also the turboprop can be used for helicopter. Okay, the propeller here. Okay, so this is a turboprop engine. We add a propeller instead of fan. We have propeller and then compressor, burner are the same. Okay, this is a ramjet engine and this one we seldom use. We focus on turbojet, turbofan, turboprop. Okay. Okay. Uh, okay, we see this one. Maybe this is sekejap. Angle, backward ratio, turbojet aircraft flies. Terbaik terbaca. Turbojet. Okay lah, we see this one first. A gas turbine power plant operating. So we finish we the slides, the theory part of this chapter, gas power cycle. Okay. So maybe we look at the only one example, and then the rest we continue next week, final week, to do some revision before our final exam. So a gas turbine power plant operating on a Brayton cycle has a pressure ratio of 8. The gas temperature is 300 Kelvin at the compressor inlet and 1300 Kelvin at the turbine inlet. Assuming a compressor efficiency of 80% and a turbine efficiency of 85%, determine A, B, C. Okay, take 2 minutes. Yeah.
And doctor, are you here?
Yes, ambil sekejap. Ambil lihat sekejap.
Sorry,
Okay,
sorry.
you can start to do this exercise. Okay. So normally for gas turbine cycle or thermodynamic cycle, okay, so even though at the end we need to evaluate the performance, thermal efficiency or turbine the temperature, etc. Usually we need to start from the beginning, from the first point, from the first process, which is compression, and then combustion process, and then expansion, and complete the cycle. Then we will get the cycle efficiency or the cycle network output. Okay, so usually we will have to start from the beginning, even though it doesn't ask you to calculate the work pressure, compression work, etc. But we need to start from the first point location. Okay. So it is better once you got the problem, we try to sketch the cycle in a TS diagram or PV diagram, but usually we use TS diagram. Okay, so that you know where is your location 1 to 2, the compression, etc., etc. Okay, you define first that. So for this one, for this one, we need to calculate the back work ratio. Okay. The compressor work and the work is done in the compressor and turbine. Okay. So we need those to calculate the work at those point lah, compressor and turbine. Okay, so in order to calculate compressor and turbine, we need to know the location. Okay, tengok satu. Okay. Okay, so first A. So of course we need the compressor work and the turbine work. Okay, so from the definition, compressor work, we can use, okay, the energy balance at each of the component device. So for example, in the compressor, we know that the energy balance, the first law, energy balance, we only have work, okay, work done or work input in the compressor. We don't have heat transfer, etc. So directly compressor point H2 to H1. This is the, for example, TS diagram of the gas turbine. Okay, ideal case, we have something like this. Okay, we have something like this. So 1 to 2, this is 1 to 2 is the compression process. Okay, so in the compressor device, there's no heat exchange, no heat transfer, no heat exchange, no heat transfer. In the compressor device, no heat exchange, no heat transfer. Okay, so energy balance will become only work and enthalpy, of course. Okay, no heat transfer, no heat exchange, no kinetic energy, no potential energy. So this is what the energy balance become. Okay, and work turbine, 3 to 4. Okay, 3 to 4. So H3, we start with H3 because H3 has higher temperature, 3, 4, because we want a positive value. So H2 minus H1 and H3 minus H4. Okay. Because the plant operating on a brighter cycle has a pressure ratio of 8. Oh, we can use pressure ratio 8. The gas temperature is 300 Kelvin at the compressor inlet. So T1 is 300 Kelvin. And 1300 Kelvin at the turbine inlet. So T3 1300 Kelvin. Assuming compressor efficiency of 80%, turbine efficiency 85%. So this is okay. Compressor efficiency 0.8 and turbine efficiency 0.85. Okay. Okay, so we know T1 300 Kelvin. So we assume that the gas turbine power plant use air as working fluid, and the air is ideal gas. Okay, ideal gas, air, vapor. So we can use a table to search for H1. From T1, we can get H1. Okay, wait table. Table. Ideal gas. Okay, table A17 ideal gas. So at 300 Kelvin, you have enthalpy 300.19 kilojoule per kilogram. Use your table, ideal gas table. Okay, so you have H1, and from the same level, for the same table at temperature 300 Kelvin, we is stated also the pressure ratio in the table, thermodynamic table. If you look at the table A17, so you can take that pressure ratio PR1 from the same level 1.386. 1.386. Okay, because since given here the pressure ratio of 8, I know this is not pressure ratio. Okay, the PR first. Okay, so we use this value to get the T2 later on. Okay. Okay, so here so this has no unit. So so we have this enthalpy. We want to search for temperature, and then we can get the H2 using the same table. Okay. So we have PR2, the ratio of the ratio of PR2 over P1. PR1 is equals to P2 over P1. Okay, and this is equals to, this ratio is equals to 8. Okay, so knowing this, PR okay, so 8 times 1.386, you get the PR2. Okay, so this using the PR2, we will get the temperature back. Okay, using the same table, table A17 for ideal gas. A 70, ideal gas. Okay, so 1.386 multiplied with A around, you get around 11. Okay, 11 PR2. So go back to the table. If you look at the 11, around 11 PR2, you have temperature 540 Kelvin. Okay, using the same table. Okay, calculate back PR2, knowing the ratio 8. Okay, so you and we get 11, and we search in the table. The value PR11 is when we have temperature at 540 Kelvin. Okay, so with at the same level at 540 Kelvin, we have H2. So they're quite small. H2 544 3.35. 544.35 kilojoule per kilogram. Okay, so knowing H2, H1, we can calculate the compressor work. Okay, so the same thing can be done for turbine work. Okay, so we know T3 1300 kelvins. We search for H3 using the same table. So H3 1300, table A17 1300, H3 1395.97, 1395.97, and the PR assumed here is 330.9 or 331. And then we using the ratio, but this time around for turbine, the ratio is the opposite. So 1/8, because turbine opposite. Okay, 3 to 4, the ratio. So 1/8. So we get PR4. And with that PR4, we get T4 and H4. So the same method is just the reverse back. Okay, the ratio reverse. Okay, so we get the H3 and H4, and that's how we calculate the turbine work. So the compressor work is around 244 kilojoule per kilogram, and the turbine work is around 306.6 kilojoule per kilogram using the same method. So just do the same method like for compressor, using the same method, starting from the temperature inlet turbine 1300 Kelvin, you search for H3, PR3, and the ratio, and then PR4, T2, H4. Okay, so and then you get the also once we get here, we for work back work ratio, just compressor over turbine. Okay, the ratio of the compressor work over turbine. So we get the backward ratio around 0.4. This one, 0.4. Okay. Okay. Second one, before we finish, 5 minutes more. Okay, second one, thermal efficiency. So say we have started the initial calculation is easier later on. After that, thermal efficiency, I think, okay, so thermal efficiency, W net over Q in. Okay, the W net is the one that we have calculated just now. So the work turbine minus work compressor. Just for Q in, we have all the H3, H4, H2, etc. So Q in is H3 minus H2. Okay, so you already have the value of H3, H2 previously, so just use that, and then you get the thermal efficiency. So that is B. So easier. Okay. B, C, turbine exit temperature. Okay. How do I put turbine exit temperature? Okay, because it's okay. Okay, so we use turbine exit temperature. Turbine exit temperature just now you have WT. Actually we can already get from this one, from this method. Will be H4 H3 minus H4. Okay, and we can use this one. Either this one is CP T3 minus T4. Okay, because we have assumed that is either gas, etc. So this one is 1.005. Okay, T3 just now 1300 Kelvin. So this is T4. WT 606 kilojoule. This is also in kilojoule. So we get T4. Okay. Okay. So that is example for gas turbine power plant using Brayton cycle. Okay, so so next week we continue with the other example. Okay, if maybe I add more example, and the one that we haven't finished last week, there are 2 more questions that we haven't finished last week. We can see that as well. Okay, so next week, last week, final week before your study week and final exam. So we will do revisions, okay, to prepare for your final exam. Okay, we will do tutorial. We have finished the lecture. We have finished all the chapter. We will do only revision next week, insyaAllah. Okay. Okay. Okay, everyone. Okay. Okay. So that's all from me. So I'll see you guys next week, insyaAllah. Thank you very much.
Thank you, Doctor.